Here we go. So guys, as I mentioned to you when we started into this unit, you guys are sort of at a disadvantage. I've already accounted for it in terms of the schedule. But guys, because of all the craziness of last year, something had to give. And so last year in general chemistry, never mind, it doesn't matter. We had to skip this 2 years ago too, because 2 years ago, I was teaching from home last spring. Oh, shoot. Okay. So guys, it doesn't matter when you took general chemistry. You missed this. We did not do the gas unit for the last 2 years. 2 years ago, it's because we were at home, walked out of school. Last year, it's because we ran out of time because of all the AKLZ stuff that we had to do. So guys, in either case, you haven't seen gases. With that said, you are not completely in the dark because you've all seen this. So guys, as we talked about before, we didn't do the unit on gases. We didn't quantify gases. We didn't do a deep dive on the behavior of gases. But we did do this. Last year and the year before, we did differentiate between solids and liquids and gases. We talked about the idea that solids are low energy, high density substances, low temperatures. They don't take on the shapes of their containers. They are bound together in very neat, organized structures, low entropy. Guys, those are solids. Then as we add energy, the solids break down. The intermolecular forces don't break, but the structure breaks down, and we end up in a liquid state. Liquids are still bound by intermolecular forces. The thing that's missing is the structure. Their energy is a little higher. Their densities are a little lower than solids, unless you're water, and then the densities flip. And guys, these things do take on the shapes of their containers. They still have intermolecular forces. And then guys, we get into gases. You take a liquid, you heat it up, you break the intermolecular forces. Now we're a gas. Guys, high energy, low density. They not only take on the shapes of their containers, they take on the volumes of their containers. Guys, liquid water only fills the portion of the beaker that it has enough water to fill. I could fill this with water and you'd see it would be at the bottom. Guys, gases completely fill their spaces. They take on the volumes of their containers because they don't have intermolecular forces. So guys, all of this to say you do understand some things about gases because we looked at them at least generically. Today what we're going to do is we're going to dig into them at greater depth. You guys ready to go? Here we go. So guys, this then is where we're going to start. Guys, when we talk about gases, this you want to write down with me. Ideal gases. And then be very judicious about where, I'll tell you when to write things down. But guys, ideal gases is a critical idea, so let me explain. So guys, here's the deal. Gases are very complicated. There's a term that we use for that. Guys, gases are very, do you guys actually know the technical mathematical term for complicated? It's chaotic. Guys, gases are literally chaotic systems. And chaotic, guys, in a technical sense, doesn't mean a mess. Chaotic means it's so complicated that it defies study. And guys, it doesn't take much to be chaotic. You should understand this. If you guys all played pool, rack them up, break them with the ball, pool. Okay, here's the deal. If you've got the cue ball, and if you've got one ball on the table, if you know the force with which you hit the ball, and if you know the masses of the balls, and if you know the angle that they hit, guys, you can predict with absolute precision where the two balls are going to end up every single time. That is not a chaotic system. Because here's the deal. If you do this, if you take your pool table and if you simply put two balls there and one ball there, and if you know all the same information, mass, force, angle, everything else, By simply adding one more ball, this becomes chaotic, and it is absolutely impossible to figure out where these 3 balls are going to end up. Guys, the question is why? And the answer is because there are interactions between these 3 balls. When they hit, very, very small differences in the way that they impact each other has radical implications on how this all ends up. So now, guys, imagine what's going on inside of a balloon of gas. Guys, can you picture what these particles are doing? What are they doing? What are gas particles doing inside this balloon? They're flying around hundreds of miles an hour. Can we make them go faster? Sure, heat them up. Can we make them go slower? Cool them down. But guys, as they're flying around, what are they experiencing? They're running into each other. What else? Running into the side of the balloon. That's why they push out and it creates pressure, because literally the molecules are pushing out. But guys, the deal is this. There are an uncountable number of molecules inside this balloon. It's my breath. But whatever the gases are inside of here, guys, this is absolutely chaotic. It defies study because it's so complicated. You get the idea? So guys, the question is, how do we fix this? And the answer is, we go to the land of make-believe. And guys, this is not stupid and this is not dumbed down. This is smart science. If you've got a system that's so complicated that you can't study it, what do? You simplify the system. And guys, that's what ideal gases are. Ideal gases are simplified gases that make our lives easier. Now guys, be clear. Do ideal gases really exist? No, but we treat them as if they exist. And what allows this to be the case? Don't write this down. Oh, shoot. Guys, don't write this down until I tell you. So guys, it goes like this. The thought is this. When we study gases, these things are so complicated, they're bordering on impossible to study. So being good scientists, we come up with more simple models. Guys, the thing that allows this to work is the use of these more simple models not only allows us to describe them, the math doesn't change very much. So these simplified models don't create significant changes in our results. So guys, the question then becomes this, and this is where you want to start writing this down. What are the simplifications that make the model appropriately less complex? And guys, it's this. There are 2 simplifications. You need to understand them. Simplification number 1. So ideal gases are gases composed of particles with ... Oversimplification number 1, mass but no volume. That is oversimplification number 1. They have mass but no volume. So guys, what does this mean? What does it mean to have mass but no volume? What does it mean to have mass? You exist. You have weight. You're there. You're matter. You matter. But guys, what does it mean to not have volume? You don't take up space. Can you be there and not take up space? No. This is make-believe. But guys, here's the deal. This is actually an important simplification, but it's also appropriate. And this is why it's appropriate. If you could see inside of a sample of gas, those molecules are so spread out that the size of the molecules themselves doesn't really matter. The word that we use is insignificant. That's the word you want to use on the test. The molecules inside of a gas are so spread out that the size of the molecules themselves doesn't really matter. So guys, let me give you an analogy that's going to help you understand this. Guys, I grew up in a really, really small town in Wyoming. And in this really small town in Wyoming, our homes were all spread out. Like it was a purposeful walk to go see my neighbors. But guys, here's the deal. So this town that I grew up in had a border, right? Here's the town. This is the size of the town. But guys, all of our homes were really spread out. So guys, imagine this. Imagine if me and all of my neighbors in this little town all of a sudden won the lottery and we had all of this money and we all ripped down our homes and built bigger homes. Would the boundary of the city have gotten bigger? Why not? Our homes are bigger, so why doesn't the city get bigger? Because there's so much space around our homes that our homes getting a little bit bigger was insignificant compared to the size of the city because of all the free space around us. Does that make sense? Gases are the same way. Guys, if you look inside of a gas, you've got molecules inside of here that have so much empty space around them because they're so spread out. There's so much empty space that the molecules, the size of the molecules doesn't really matter. They could be small, they could be big. The size of the molecules is insignificant. Does that now make sense? Okay, remember the analogy. Then guys, number 2 is this. These have no intermolecular forces. Gases have no intermolecular forces. And guys, this should cause you trouble because you should be thinking to yourself, wait a minute, you just told us on the previous slide that gases don't have intermolecular forces. Guys, this is actually not completely true. How do we know that it's not completely true? Guys, the way that we know that it's not completely true is because we can take gases and turn them into liquids. This is liquid air. And so guys, if gas couldn't, if it didn't have intermolecular forces, we couldn't liquefy it. So guys, why is it that we can say that gases don't have intermolecular forces? Well guys, imagine steam. And inside steam, we've got a water molecule there and a water molecule there. Are these things still polar? Yeah, but why aren't they attracted to each other? They're so far apart. So guys, these molecules still can have intermolecular forces. The difference is they're so spread apart. But now guys, put them in motion inside of a balloon, and every now and then what do? They hit each other. And when they do, they instantaneously stick. And then they bounce off. So what we do is we pretend that they never stick. No matter how close together they get, they never stick. And guys, the thing that allows this to be reasonable is that the gas molecules are so spread out that they cannot attract each other. But guys, we do know that they do in fact come close to each other at times. But what we say is that no matter how close together they get, they never stick. So guys, the interesting application of this is an ideal gas can never be liquefied. Did you catch that? An ideal gas can never be liquefied because in theory it never has intermolecular forces, and as a result they never stick together. Okay, so guys, this then provides the foundational understanding that this entire deal is based on. That for us to understand gases, we're going to pretend like they're there but they don't take up space, and we're also going to pretend like they're never sticky. You guys good? Okay, so then guys, from there, what we need to do is we need to define some terms and some ideas. You guys all caught up with me? Okay, so guys, when we do this, we've got to talk about STP. You guys know about this? No? Standard temperature and pressure. Guys, for us to study gases, we need to establish standards for temperature and pressure. Why? Because gases are very susceptible to change based on temperature and pressure. So guys, in order for us to don't need to write this down. In order for us to study gases, we've got to determine some standards for temperature and pressure. So again, temperature and pressure, let's do standards for each. So guys, first of all, standard temperature, write this down. Guys, standard temperature is defined as the freezing point of water. So when we talk about standard temperature, that is 0 degrees Celsius, which is also 273 Kelvin. Now I need to ask another question. Do you guys know about the Kelvin temperature scale, or should we go over it quickly? Go over it? Okay. So first of all, this. In order to convert from Kelvin, Celsius to Kelvin, all you have to do is add 273. So guys, let me explain to you the difference between the scales. Please don't write this down, just watch. So guys, it goes like this. What we have here are 3 different temperature scales, Fahrenheit, Celsius, and Kelvin. Relative to water, we've got the boiling point and the freezing point of water, and then proportionally, we've got what's called absolute zero. Do you guys know about absolute zero? What happens at absolute zero? Nothing. This is the point where all motion stops. You guys understand that even inside of something like ice, guys, even inside of ice, these molecules are locked in place, but they're still vibrating. At absolute zero, 0 Kelvin, they stop moving. You guys know that, right? Okay, so, sorry. No, my bad. Okay, so guys, let's then put these numbers on the scale. So guys, did I have this animated? Oh, I don't. I'm going to have to write it in. Shoot, that means I have to remember the numbers. There's only one I don't know. Okay. But we could figure it out, but I don't want to. So guys, Fahrenheit, because that's where we live. Fahrenheit, because that's where we live. Water freezes at 32, and it boils at 212. Ridiculous, right? By the way, do you know where those numbers came from? Fahrenheit's a guy, Lord Fahrenheit. It was actually named after a guy. Do you guys know where the numbers? Let me share with you quickly. So when Fahrenheit was setting up his scale, he was looking like we do to calibrate his thermometer, and he was looking for fixed points. And the fixed points that he used were actually here and here. So his fixed point for the high temperature was body temperature, and he called that 100 Fahrenheit. He was a little off. It was 98.6, but given his thermometer, that's not too bad. But then, guys, his 0 point was actually the coldest temperature 250 years ago that he could create, which was actually the freezing point of saturated salt water. So he took salt water and he saturated it with table salt, and then he froze it, and he said that's 0. What we know from colligative properties, we know that pure water freezes at 32, and adding the salt made the freezing point go down. So he established 0 as the freezing point of saturated salt water, 100 was body temperature, and then using that scale, water boils at 212 and pure water freezes at 32. Complete train wreck, right? Okay, so now guys, let's go to the Celsius scale. Whole lot more sense. This is 0, this is 100. Now we're getting somewhere. But guys, on that scale, absolute 0 is negative 273.15 something, doesn't matter. It's 273 degrees below 0. That's pretty chilly. But guys, when we study gases, we do not use the Celsius scale. We'll talk more about why when we get together on Friday, but we need the Kelvin scale. So guys, let's talk about Kelvin. The Kelvin scale and the Celsius scale are exactly the same scale. The only difference is the 0 point. In Celsius, 0 is the freezing point of water. In Kelvin, what's the 0 point? Absolute 0. So this becomes 0, this becomes 273, and this becomes 373. So guys, the only difference is the 0 point. Now guys, with that said, just really briefly, just so we do this well, guys, understand that there is no such thing as a degree Kelvin. Don't ever in college say degrees Kelvin. Your professors will nail you to the wall. Here's why. Guys, degrees mean a separation between points. 90 degrees are the number of divisions between a right angle. So guys, degrees mean division. So these are Celsius degrees because there's 100 of them between freezing and boiling. Guys, there are no Kelvin degrees because Kelvin is defined as starting at absolute zero, and as a result, Kelvin degrees are not a range between 2 points. It starts at zero and it goes up from there, and because there is not a range, we don't say Kelvin degrees, we just say Kelvin. I know that seems subtle, but someday it'll matter. So, you guys good on all of this? Okay, so guys, moving back then, we've got this, and that is why Kelvin is Celsius plus 273. Good? Okay. Then guys, standard pressure. Standard pressure is defined as the pressure at sea level on an average day. I know that sounds amazingly wishy-washy, but we've collected a lot of data, and we know what the pressure is on average at sea level. So, guys, and we did the barometer talk already, right? You on your phones. Okay. So, guys, let's put it in context. The units are the one that you're probably familiar with, PSI. You inflate your car tires to 30 PSI. I inflate my bike tires to about 80 PSI. In PSI, standard pressure is about 14.5. We'll never use those units. Guys, we will use these. Millimeters of mercury, which are also called torr. We'll explain that more on Friday. Then, guys, conveniently, this is also equal to 1 atmosphere, which sounds ridiculous, but that's actually a measurement and not a name. We do measure things in atmospheres. And then finally, there's another unit, which is the Kilopascal, named after our good friend Blaise Pascal, who not only came up with a triangle, he also did some science. And do you guys know Pascal's triangle? Okay, yeah, same dude. What if your first name was Blaise? That's pretty sweet. All right, and so guys, that's another unit that we use. It's really small, so we use kilopascals just because it's so small, it's almost worthless. But that's the idea. You guys good? Okay, so here then is where we are. We're done laying the framework. So guys, this then is what we're going to do. Why do we establish a standard temperature and a standard pressure? And guys, the answer is because gases change, specifically their volumes. But guys, gases change when you change the temperature and when you change the pressure. And guys, I'm going to be honest with you. This is the most disappointing moment you're ever going to have in this class. It is so disgustingly obvious that you're going to feel good about yourself because you're like, oh, hey, these things have names. This must be cool. And guys, they're kind of ridiculous. Check it out. So, what we're now going to do is we're going to talk about how these factors impact the behaviors of gases. And guys, we are now going to talk about, write it down, Charles' law. Oh yeah, Charles. I think he might have been a prince. I don't know. Fahrenheit was a lord. This guy was something. So guys, Charles' law, right? The dude got to name the law. It's a law, Charles' law. You ready for Charles' law? You heat up a gas and it gets bigger. Guys, seriously, but there's another part. You cool down a gas and it gets smaller. Guys, that's it. But we got to make it sound important, so we're going to say this. Ready? The volume of a gas at constant pressure varies directly with temperature. Because all that means is you get a gas hot and it gets bigger. And if you get a gas cold, wait for it, it gets smaller. Oh yeah. Guys, the only reason Charles got to name this is because 200 years ago, that was a big deal. Now it's just kind of duh. But by the way, guys, we should talk about why. Why does heating up a gas make it bigger? At a molecular level, what's going on? Molecules are moving faster, they have more kinetic energy, and they spread out. And then if you cool them down, less kinetic energy, they slow down, they come together. So, guys, if this is in any way confusing to you, you ready? Don't write this down. When temperature goes up, the volume goes, oh yeah, up. And when the temperature goes down, the volume goes down, huh? But you're going, wait, this is stupid. Largely because I'm making it sound stupid. But guys, the implications are interesting. Tomorrow morning, when you get up, if you can see your tires, because there's the possibility they're going to be buried in the snow. Seriously. Yeah, we have 3 to 5 inches coming by tomorrow night. But guys, when you go out and you see your tires on your car, guys, you did not just get punked, because your tires are going to look flat. Somebody did not just come along and let the air out of your tires. Why do your tires look flat? Because they got cold. And Charles' law said the molecules slowed down and they contracted. But guys, here's the magic bit. Don't put air in your tires, drive to school, and by the time you get to school, your tires are going to reinflate. Why? The temperature of your tires goes up because, guys, the rolling friction between your tires and the road heats your tires up, which heats the gas up, and then the gas expands and it reinflates your tires. Get the idea? Now, guys, did you know this? Scares me if you don't, so don't admit it. When you open the driver's door of your car, there's a sticker on the frame of the door that tells you the temperature you should inflate your tires to. But you'll notice that it says cold tire pressure. Why does it matter? Because if your tires are warm, the pressures will be higher. So the only thing they can do is define what pressure should be in the tires when your tires are cold. And by that they mean you haven't driven for 3 or 4 hours. That's the only fixed point that they can define. So if you go to put air in your tires and you've driven your car around, the pressure will be higher, and that's going to throw off the reading. Do you get the idea? Okay. All right, then guys, hot air balloons. You guys know how these work? Wait, shoot. Oh no, we have time to do this. Hot air balloons. So guys, think about what does this have to do with Charles' law? Well, we've got heat. And if we've got heat, what have we got? Expansion. So why does the hot air balloon not blow up? Do you know? Because there's a vent in the top. Do you guys not know this? So guys, the idea is this. If you've ever been in a hot air balloon, the pilot pulls a lever that fires the burner. But at the same time, they also pull a rope, which puts a disgustingly huge gaping hole in the top of the balloon. Literally, you can look up and see the sky. Terrifying. But guys, if they didn't do that, the balloon would expand and it would pop. So what they do is they open the vent in the top of what they call the envelope, the balloon, and when they fire the burner, the gas expands, but now it has somewhere to go. And it goes out through the hole, and when they shut off the burner, they also close the flap. And now the gas that's still trapped inside the balloon has a lower density because the gas spread out, and that makes the balloon buoyant and it floats. Yeah. Normally propane. I believe it's always, I've only once, but I think it's a propane tank, but I'm not sure. Balloons, good? Okay, so guys, Charles' law, it gets better. Boyle's law. Boyle. B-O-Y-L-E. Don't confuse them. All right, you ready, guys? Hold on, life-changing stuff coming at you. Ready? If you take a balloon and squeeze it, wait for it, it gets smaller. Oh yeah, that's Boyle's law. But you ready for this? What if we could take a balloon and squeeze it less? It gets bigger. Come on, Boyle. Can I do the voice again? So it says this. The volume of a gas, this is like my Kathy voice. The volume of a gas varies inversely with pressure. That didn't go as well. But guys, really it's this simple. Ready? If pressure goes up, the volume goes down. And if pressure goes down, the volume goes up. But guys, understand, we're talking about the pressure around the gas, not the pressure of the gas. So this is the pressure of the things surrounding the gas. We'll relate them on Friday, but it's the pressure around. So, again, some examples. Consider this. Do you guys know what this is? This is actually a weather balloon. This is not a hot air balloon, guys, but this is a buoyant balloon. But instead of this floating because it's full of hot air, guys, this is a balloon that floats because it's full of a gas that is already less dense than air. It's helium. Now, here's the deal. This weather balloon, and you guys understand there are dozens and hundreds of these floating around in our atmosphere all the time. But guys, this weather balloon is fully inflated and ready to go. This is not in the process of being inflated. It's done. Why don't they fully inflate it? So guys, think about it. When we cut the tethers and we let this balloon go, it's going to go up. And as this balloon goes up, what happens to the density of the atmosphere as we go up in it? The density goes down, so there's less pressure. That's why your ears pop when you drive up into the mountains. So guys, there's less pressure as we go up, and as the pressure goes down, what does Boyle's law say is going to happen to the size of that balloon? It's going to get bigger. So guys, the idea is that if we launch these balloons fully inflated, as they go up, there's less pressure, and if that balloon is already inflated, it's going to pop. So it's actually masterful what they can do. They calculate the amount of gas that they need to put in this balloon to get it to become neutrally buoyant at exactly the altitude they want it to hover at. So as the gas expands, the balloon becomes bigger and the density goes down, and eventually the density inside the balloon becomes the same as the density outside the balloon. We call that neutrally buoyant, and at that point it floats. And they can do the math. Knowing the mass of the helium and knowing the size of the envelope, they can figure out the density at any altitude because they know the pressure, and they can figure out how much gas to add to make it hover where they want it. Pretty good, right? But guys, what if we go the other direction, and what if we increase the pressure? You guys have all had this experience if you've ever dove to the bottom of the diving well in a swimming pool. And guys, you know that when you get down there, it feels like your head's going to explode. But it's not going to explode, it's going to implode. Literally, your head is being crushed by all the water. But guys, why does that hurt? And the reason is because you've actually got air trapped behind your eardrums. You've got these tubes called the station tubes that allow the air to get in and out. And you've got air trapped behind your eardrums. And guys, as the water compresses your eardrums, it compresses the gas underneath your eardrums. And guys, it creates pressure inside of there that hurts. So what do you do to fix the problem? You grab your nose and blow. And when you do, it pushes out and it equilibrates the pressure inside and outside your ears, and the pain goes away. So guys, if you've ever made the mistake of like going up into the mountains when you have a head cold, you know how that is where your ears hurt and there's nothing you can do to get it to get better? The reason is because that cold caused your eustachian tubes to swell, and they're swelled shut, and the air can't get in and out, and there's nothing you can do to equilibrate the pressure other than go back to where you came from where the pressure's the same. Huh? Boyle's law? You guys good? Okay, so guys, all of this then leads us to what is called the combined gas law. Guys, write this down with me. This is what is called the combined gas law. So guys, not surprisingly, there is a relationship. Don't write this down. Guys, there is a relationship between temperature and pressure and volume. And guys, the relationship is this. Write it down. P1 V1 over T1 is equal to P2 over V2 over T2. So guys, what does this allow us to do? And the answer is this. If we allow this to be the initial conditions, and if we allow this to be some new set of conditions, we can figure out how any one of these three things changes based upon the other two either changing or staying the same. Now guys, here's the deal. What if we had a problem that said something like this? You have a gas. Let's actually write it. I'll write it down. So guys, imagine that we have a problem that says this. You have 100 milliliters of a gas at 20 degrees Celsius. What will the volume be at 50 degrees Celsius? And these are Celsius. So guys, we have 100 milliliters of gas at 20. What will the volume be at 50? What's the answer? Bigger or smaller? Come on guys, we laughed at Charles, but now you got to know it. It's 20 degrees is 100 milliliters. What will it be at 50? Bigger. You don't get to laugh at Charles if you can't say bigger. Because guys, we know the volume at 20. If the volume goes up to 50, if you don't understand that the gas gets bigger, you got to stop laughing at Charles and actually make sense of it. It's going to be bigger. Guys, the question is this. How much bigger? And we can calculate that. Let me show you how. Guys, first of all this. We get rid of pressure. Why do we get rid of pressure? Because we assume that it's not changing, because they didn't say anything about it changing. Then here's what we know. We know the volume, and I'm going to write in this direction. We know the volume at what temperature? Not 20 degrees Celsius. 293 Kelvin. You've got to convert to Kelvin. Now what we want to know is the volume, but we want to know the volume at what temperature? 50. And that would be 323. And guys, I'm pretty sure that even my algebra skills will allow us to solve this. So I don't know how you get there, but I would go 100 times 323, then divided by 293. And guys, this answer had better be bigger than 100, and I get 110. So I can say with a pretty good degree of certainty that's right because it's bigger. Now guys, understand we can solve this equation in any possible direction. And this is called the combined gas law. You guys good? We got one more thing to do, and it's very important. Here we go. Write this down. Remember our good buddy Avogadro? If you don't remember, he has a number named after him. It's a big number. It's 6.02 times 10 to the 23rd, and it's the number of particles in a mole. But guys, here's the thing we haven't talked about before. How did Avogadro come up with his number? And guys, the answer is he was studying gases. And Avogadro, while he was studying gases, came up with a really, really interesting idea. Guys, do not write this down. But here's the idea. You're going to remember this when you get to college, and you can use it to share with your friends. So guys, we're going to lay out a hypothesis. And the hypothesis is this. Guys, we've got a 30-gallon trash can, a 30-gallon trash can in front of the class. And I want you to make some estimates. I've actually done it. But guys, if we were to fill this trash can with tennis balls, and frankly, I didn't actually fill it with tennis balls, but I did the math. Guys, how many tennis balls would it take to fill that bucket? What'd you say? Autumn. Yeah, Autumn. Come on. We're going to trust Autumn.
I don't know. I don't even know how many tennis balls fit in my basket.
More than 10.
Yes.
All right. Guys, actually, the answer is somewhere on the order of about 180 tennis balls. But guys, this. How many volleyballs? Are any of you? I know, I was like, wait, am I the only volleyball person? No, it was actually, well, it was 9. But it was hard because I couldn't get them exactly flush. But guys, you ready for the earth-shaking idea? Why does it take more tennis balls to fill the bucket than volleyballs? Because tennis balls are smaller. Ready? So guys, we are now saying something earth-shattering. It takes more small things to fill a bucket than it does big things. Now, let's take the same logic and let's apply it to this. Guys, here I have 2 balloons. We are going to say that these balloons have the same volume, and we're also going to say that they contain gases that you know they don't because you saw me blow them up. But guys, we're going to say this. We're going to say that this balloon contains hydrogen gas and that this balloon contains C3H8, which is butane, which is the gas in Bic lighters. So guys, let's do this. So guys, this is what we're saying. This balloon on your left, my right, contains butane, which looks like this. This balloon on your right, my left, contains hydrogen molecules. Which one's bigger? Butane or hydrogen? Butane. So, which one contains more molecules? The hydrogen or the butane? Hydrogen. Why hydrogen? Because they're smaller and therefore it takes more molecules to fill them up, right? Completely wrong. Completely wrong. And this is Avogadro's hypothesis. Guys, write it down with me. 2 similar gases will contain the same number of molecules because, guys, the particles are not in contact but rapidly moving objects. So as you're writing this down, let me show you. Seriously. Have you ever thought about how much easier your life would be if people around you weren't stupid? I think about that a lot. Spencer, don't be offended. That's true. So guys, let me show you what we're talking about. So, we are going to allow airsoft pellets to represent small molecules, and we are going to allow ping pong balls to represent our butane, our big molecules. So guys, here we go. This is a beaker full of big balls. This is a beaker full of small ones. And guys, we can clearly see that it takes more small things to fill up the beaker than it does big things, right? So why isn't this true of gas molecules? And the answer is because this isn't what gas molecules look like. Guys, what phase is this most representative of? Liquids or maybe solids? So guys, what is actually going on inside of a gas? This would have been much easier had some idiot not ripped up my parafilm, but I'm going to try this. Guys, this is actually what's going on inside of a gas. These things are moving around randomly and chaotically, and the only reason they fill the space is because they're moving. Well, guess what? These are also moving randomly and chaotically, and the only reason they fill the space is because they're moving. And guys, just like my house in Wyoming, if it got bigger, it doesn't make the city bigger. The same thing's going on here. The size of these particles compared to the space around them is insignificant. So as a result, it doesn't matter whether you've got a balloon full of hydrogen or you've got a balloon full of butane. There's exactly the same number of particles because the size of the particles doesn't matter in the first place. Do you get the idea? But guys, understand, completely counterintuitive, right? If you're thinking this is what gases look like, your mind is blown. But if you understand that these gases aren't like that and they're all spread out and the size of them doesn't really matter, then this makes sense. You good on the idea? Okay, so guys, where do we go with this? What's up, Britt? No, I wanted to talk to you about that. Can we talk in... Yeah, is that okay? But no, I don't believe we did. So guys, this then becomes the question, what does it mean to be similar? Do not write this down. What does it mean to be similar? And the answer is this. In order for our balloon analogy to be the case, these have got to be at the same pressure. Guys, don't write this down. These have got to be at the same pressure. Now guys, how do we know that these two gases are at the same pressure? Because they're in the same room. This gas is being squeezed by the same atmosphere as this. Now they're not at the same pressure. We can't tell the difference because it's not that different, but the higher you go, the lower the pressure. But if they're like this, they're at the same pressure. They also have to be at the same temperature. But guess what? They are. What temperature? Room temperature. Guys, they also have to have the same volume. This one shrank a little, but we'll call it close. But guys, this then leads us to an equation. This you want to write down. This is what is lovingly called the Pivnert Equation. And guys, it says this, V(nRT). This is called the ideal gas equation. It's important enough that an old AP class of mine put it on a hat. But guys, look at what we've got here. Are you ready? All the pieces are about to fit together. What's P? Pressure. What's V? Volume. What's T? Temperature. What's R? R is the universal gas constant. So guys, P is pressure in atmospheres. V is volume in liters. By the way, this is all on your AP cheat sheet, but you're welcome to write it down. N is actually number of moles. Hey, there's Avogadro. R is the universal gas constant. Its value is 0.08206. Notice the units, liters, atmospheres per mole Kelvin. And then guys, temperature's got to be in Kelvin. Class of 2000, wow, 11. This is 10 years old. Look at that. That's crazy. Did you hear the bell, Diana? Did you get done?
No.
I'll just leave them there, and if you could finish them up. Thank you. Just a second. So guys, here's where we're at. I'm going to leave this there. Understand the idea is there's 4 variables: pressure, volume, number of moles, and temperature. R is a constant. If you're given 3, you can solve for the 4th. That'll be in your homework. And it is on the equation sheet as well. So guys, this is your homework. We're going to stop there and take a break. Santiago, however, is going to lead us into break with a question.
So the question is, if the gases
Yes.
take a volume of their container,
Mm-hmm.
why do we care about the volume?
Because it changes. So, for example, if you've got the Pivnert Equation, better way to explain it. So, what if this balloon was half as big? So if the balloon is half as big, it's no longer the same number of particles. It's actually half as many particles. But the idea is that in order for Avogadro's principle, which is same number of particles, to hold true, the volumes have got to be the same. Because if they're at the same temperature and pressure and the volume is smaller, then the number of moles is smaller. Is that okay? Yeah. No, so they let me do this really quickly and then we'll take a break. So where do the units come from? Well, and we're going to do this in lab after Christmas. We're actually going to measure the universal gas constant. But if you solve this for R, it actually looks like this. So divide by PV, move R. No. So no, it's not. That's backwards. So PV is equal to nRT. Let's just do this. PV divided by NT. That's the easier way to do it. So these are the units. It's liters, kilopascal, no, liters, atmospheres per mole Kelvin. That's where the units come from. If you don't label your numbers, you're fine. Okay. You guys ready to take a break? Okay, we'll see you after break. And guys, we're going to grade homework when we get back.